that is going to figure in the mathematics that we're slowly going to create here. We've already seen some examples of it, but we need to readjust our thinking a little bit, because the way we think about nothing currently in mathematics is subtly and quite distinctively different from what I'm advocating here. So we have to get on top of nothing. We'll do that in our next video. I'll go join me for that. I'm Norman Robert. Thanks for listening. Today, I'm Norman Robert. In today's video, we're going to move towards reconsidering natural numbers. This is, of course, a very fundamental part of mathematics, and it's actually how we started this series some years ago. But now, with our investigation of really big numbers and really big arithmetic that goes with those big numbers, we've started to see that maybe there's room for consideration, again, of what a natural number actually is. So here are some questions that will motivate us. First of all, what exactly is a natural number? Can we say precisely, concretely, logically what a natural number is? Should we distinguish between different types of natural numbers? Maybe there's some reason for separating the different kinds of things that we've been currently grouping together in one big box into separate boxes and looking at things a little bit more finely. And should we distinguish between natural numbers and arithmetical expressions? Arithmetical expressions can evaluate your numbers, but there's some reason to believe that we should treat them as essentially something separate from the numbers that they evaluate to. So, in thinking about these questions, I think it's instructive to keep in mind the words of a very well-known American mathematician, Eric Bishop, lived from 1928 to 1983, who was a pioneer in what sometimes called constructive mathematics. We're going to be talking about his work, especially when we get to calculus and analysis more. So he is a very important thinker in the 20th century, one person who realized that the status quo really needs to be moved in a different direction. But he gave a very lovely prescription here, which I think is well worth studying. He says, meaningful distinctions need to be preserved. Meaningful distinctions need to be preserved. He's talking about a situation where you're looking at something and there's different kinds of objects and there's something fundamentally different about them. And what you don't want to do is just lump them together, ignoring those fundamental differences that are actually there. You want to acknowledge those differences, those distinctions, and build them into your description of what's going on. Very sensible and very actually useful kind of dictum. So far in this course, we have treated natural numbers as belonging to one type called nat. And this has included actually quite a few different kinds of objects. So we started out by thinking of the number in a rather primitive listing of marks or strokes on a page. That's going back to some kind of Neanderthal arithmetic. And then we moved into Arabic numbers like 54,107. Which of course is very different from this. It's just a kind of object, really. And then we considered more advanced arithmetical expressions like 10 to the 300, or maybe this expression here. Or maybe something even more sophisticated with a triangle operation. Or something even more sophisticated with one of these higher hyper operations. Or maybe even something like this, where the hyper operation now is indexed with this n to the n plus 5, n to the n plus 3, something like this. It came out as a huge number, which we really have no control over, but nevertheless is something that we can write down. So this is a very wide range of possibilities, isn't it? I mean, we're starting with something really primitive and moving to something which is pretty sophisticated and really beyond our capabilities of understanding in any really kind of solid, meaningful way. And it's natural to think, well, is it just too wide a net? And I think we can acknowledge that casting such a wide net really does lead to problems. So one key problem is that most of our theorems about numbers and arithmetic start to break down and then fail as we move from small primitive numbers through to Hebrew Arabic numbers through to these mega huge mathematical arithmetical expressions for numbers. So in particular, here's a very important example having to do with primes and the fundamental theorem of arithmetic. So we all know that every natural number can be factored as a product of prime numbers in essentially a unique way. That's the fundamental theorem of arithmetic. Now, even though that's been around for thousands of years, it goes back to Euclid, it actually is a little bit problematic. In fact, it's a lot problematic once we start getting to bigger numbers. This is a curious and concerning aspect of the way things are. So prime factorization is actually a technique that only really works for small numbers. And small numbers and tier numbers, that are roughly familiar to us in our usual range of mathematical activities. A billion, a trillion, maybe a trillion, numbers like this. In this range, prime factorization is no problem. However, if it goes significantly beyond that range, into the realms that we've been exploring in our last few videos, then sadly, prime factorization weakens and ultimately breaks down. It weakens and then ultimately breaks down completely. For example, our favorite 10 trying 10 plus 23, almost surely has no well-defined prime factorization. The fundamental theorem of arithmetic does not actually work with this thing. So if we think of this as a number, then it's no longer true that every number has a prime factorization. This thing doesn't. And I'm going to talk more about this, but idea. So here is a picture of the number line from 0 or 1 up to Z, there it is up there. And the say something else. Not exactly linear scale, but this is the range that we've seen that's sort of accessible to us in terms of being able to write things down explicitly in our universe, even assuming we can. Very vast hard drives with blank scales. Now, perhaps in God's garden, in some different world, where all of these numbers were visible, we can kind of imagine that for a second, or try to imagine that for a second. It's not entirely clear if that has any meaning, but let's just play this game. So imagine that we have God's garden, and in God's garden, we have all of these numbers, and there, perhaps this number Z does have a prime factorization. And the prime factors will be lots of them, typically, and so many of them will be in our range, these ones down here. We can find some of them. For example, 3 is a prime factor of this thing. Okay, so there will be hundreds, or perhaps thousands, or perhaps trillions of factors that we actually can't find. But there will also be lots of factors which are bigger. Still much smaller than this right here. Okay, now when we look at this same factorization in our world, okay, in our world, most of these numbers here are lost to us. We cannot write them down because they're too big to fit in our universe, no matter what arithmetical system we pick or choose. In particular, most of these primes that are appearing here in this ideal factorization are not really visible to us anymore. They're completely inaccessible. So even though this number, yes, we can write it down, it only takes a little bit of room. The primes involved in factoring it, most of them are going to be completely beyond us. This is very disconcerting, right? But it's a necessary consequence of the realization that the complexity of most of these numbers, less than Z, is overwhelming from our point of view. We've seen that, right? That's what we established a few videos ago. We were talking about that. That's the consequence of this. The consequence is that prime factorization of something like Z is completely problematic. It doesn't really exist in a meaningful way. Here's a related important example of something that becomes problematic. This is Euclid's theorem about an unbounded number of primes. So Euclid proved the fact that if you have a finite number of primes, that you can always find another prime which is outside that given collection of primes. So telling us that the primes are unbounded. We can always find another one no matter how many we have. Now this is often taken in modern times to be essentially equivalent to the statement that there are an infinite number of primes. Okay, so it is commonly asserted in 20th century mathematics that there are an infinite number of primes. People, this is rubbish. Okay, it's nonsense. It's completely untrue. There are not an infinite number of frogs, there are not an infinite number of electrons, there are not an infinite number of ideas, there are not an infinite number of theorems, there are not an infinite number of people, there are not an infinite number of ghosts, there are not an infinite number of anything, including prime numbers. We can see that when we start to explore these bigger numbers. So if we never go beyond sort of the comfort zone, then we can kind of imagine that this fairy tale idea that we had just keeps on going in some kind of uniform way. But we've seen that that's very far from being the case, that we actually have a completely different experience of numbers and their arithmetic once we start seriously exploring bigger numbers. And what we've seen is that the numbers that we have control of become fewer and fewer and sparser, and they start to thin out, become ever more bizarre. And then